There's the problem on the monatomic gas, and it says a monatomic ideal gas expands isobarically. Using the first law of thermodynamics proved that the heat Q is positive, so that it is impossible for heat to flow out of the gas. No numbers are given. We're not going to calculate anything. We're actually doing a proof. This is the kind of best image that I could find, where we can see an expansion here. It doesn't, what I circled here doesn't say it's isobaric expansion, but it is an expansion. And so we're supposed to figure out that as the heat goes in, and it kind of looks like it here with the red arrow, meaning heat flows in as well. So anyway, that's what it shows, but we're in the drawing, but that's what we're supposed to prove. So I'm going to write down the ideal, not the ideal gas law, the first law of thermodynamics. I actually don't need that box. And that one would be delta U equals Q minus W. So the change in internal energy equals the heat flow minus the work that is being done. And of course, work is being done during an expansion here. For example, on the piston moves out, does work here on this one. The PV diagram kind of looks like this, with PV, and then here's the expansion, and this is isobaric because the pressure stays constant, and then the heat is calculated simply as the integral, respectively the area underneath that straight line, which means it's this rectangle here. But this one here is where we're looking at the isobaric expansion. The work, of course, is going to be positive, but I'll show that in a moment. Here's where we're supposed to figure out the Q. Is it positive or negative? Is the heat flow going in or out? So just one algebra step, Q equals delta U plus W. That this one is a plus here, and there's a plus in front of it. Doesn't mean anything because the delta U could be positive or negative, and the work could be positive or negative. This is just the algebra here. Okay, the work, as we see in the chapter, is given as P times delta V, so pressure times the change in volume, and the internal energy is given as, or the change in internal energy is given as from the previous chapter, 3/2 N R delta T, and then there's that plus in between. Okay. At this point here, we can already decide that this part here is positive because it's an expansion. The delta V here, so from going here to there, must be positive. The pressure is always above zero. There are no negative pressures, so therefore this part here, this term, is positive anyway, and now we have to figure this one out. Well, for this one, I'm going to use the ideal gas law. So I'm going to do 3/2 NR, and then instead of delta T, I'm going to write P times delta V, and I'm allowed to do that because the pressure is the same and the volume is the only one that changes, divided by NR, and then plus that P times delta V. And now we can see all these numbers are positive here. Of course, N and R divide, and here we have P delta V, here we have P delta V, and so that means that this term is positive, this term is positive, and therefore overall the heat flow is positive. And when we write a proof, we can write QED, quod erat demonstrandum, what has been shown. Also, with the delta V being positive and being positive here, that means that the temperature actually increases, which at this point we didn't know. As the gas is expanding, for example, in an adiabatic expansion, which goes very fast, where we don't have any heat flow, so the Q equals 0, the temperature actually goes down. Apparently, in an isobaric expansion, the temperature actually goes up, and that's what we showed from here to there.